Oh, hello. Well, in addition to my last two videos on how to solve non-linear ordinary differential equations, I wanted to show you how to solve a slightly more complex non-linear ordinary differential equation, such as the one in equation 1 here. So, as you can see, we've got the coefficient 2y minus 3 in brackets times d squared y by dx squared, and that's equal to dy by dx all squared. So let's crack ahead and see if we can solve this ordinary differential equation. Right, okay, so I'm going to start by letting u equal 2y minus 3. And rather than just finding du by dy, I'm going to write this as du equals 2 dy. Okay? And the reason is that I want equation 1 to be in terms of u's and x's rather than u's and y's, or u's and y's and x's. So what we can do with this last part here, du equals 2 dy, is to rewrite it as du by dx is equal to 2 dy by dx, and that therefore implies that dy by dx is equal to a half of du by dx. Okay, and why have we put it in that form? Well, because we have a d squared y by dx squared term here. So because we've got dy by dx here, we can differentiate it again and find out the corresponding expression in order to substitute it back into this equation, along with dy by dx itself, which we'll substitute in here, and we'll substitute u into the 2y minus 3 component as well. So what we do is, as I've suggested, we differentiate twice y with respect to x, and that is equal to a half times the second derivative of u with respect to x. So we get, let me make that look a little bit clearer, du by dx squared, and this means that we can substitute the dy by dx squared, which is equal to a half d squared u by dx squared, back into the original equation, equation 1, along with the dy by dx term here. So if we do this, we obtain, let me have a look at the original equation. So we've got equation 1, and this simply becomes u times a half d squared u by dx squared, and this is equal to, in brackets, a half du by dx all squared. And this can be simplified so that we can take the half outside of this bracket. So we've got u d squared u by dx squared, and that's equal to a quarter du by dx all squared, if I can write that in there. I haven't done that very neatly, so I'll do it again. Right, okay. So a quarter times du by dx all squared, and of course that simplifies. The give u d squared u by dx squared equals a half of du by dx all squared. Right, okay. Now, this is still quite complicated, so what we have to do is to use another substitution. I'm going to say let v equal du by dx, which means that dv by dx is equal to d squared u by dx squared, and this further implies that d squared u by dx squared is equal to dv over something times something over dx. Now, what is this term and this term going to be? Well, as you can see, we've got a u here. We can think of this as being the dependent variable. It's the trouble is, if we substitute dv by dx, which is here, back into this, we end up with a u, a v, and an x, and a v there. But we don't want three variables, so we use this this dependent variable u and write du there and du there in the denominator. So this becomes dv by du, I hope, times v, and that we can rewrite as v dv by du. Okay, so we now have an expression for d squared u by dx squared. I'll just rewrite it out again. D squared u by dx squared equals v dv by du. Okay, so let's just go back and label this equation as equation 2. Makes sense. So equation 2 now becomes, let's write this down. So 2 becomes, okie doke, if we substitute those in, we get u times v dv by du, because remember, that is equal to the second derivative of u with respect to x, and this is equal to a half v squared. We seem to be getting somewhere now, so let's move that up, and I'll just keep that there for now because I want to multiply this out and rearrange. So we get u v dv by du minus a half v squared equals 0, and this implies, if we, and that's the reason why we put it into that form, because we can now factor out the v term. So we've got v times u dv by du minus a half v squared. Oops, excuse me, it's a v, and that is equal to 0. Okay, so we now have v equals to 0 and u dv by du minus a half v equals 0. let's make my writing a little tidier. So let's see, we've got a half v equals 0, right? Now, I'm going to deal with the v equals 0 bit first. So we know that v equals du by dx, because we defined it like that earlier on. So this implies that du by dx is equal to 0, and if we integrate, we find that u equals some constant. We'll call that constant 1. Well, we know what u is. U is this term here. U equals 2y minus 3. So there we are. Right, so u equals 2y minus 3 is a well, it's one solution. In fact, actually, I've gone ahead of myself there. So therefore, I'll write it here to save space. Therefore, no, actually, I'll go down below. There we are. So therefore, 2y minus 3 equals c1, which implies that 2y equals 3 plus c1. Let's make that a little bit more convincing. And therefore, y equals 3 over 2 plus c1 over 2. And of course, we can factor out the half, 3 plus c1. And that, as I said before, is a special case of the general solution. Now we want to find the general solution, so we go back to, I think it's equation 2. Let's just go right back to it. Right, no, it's a little bit after that. So let me see, where are we? Yeah, we want to now work out this bit and integrate that. So let's go back to where we were, and so we've got u and u dv by du minus a half of v equals 0. Right, now what I'm going to do is I'm going to separate the variables. Right, separate the variables, and if we do that, let's just so if we do that, we've got u dv by du is equal to a half of v, and of course all we need to do now is divide both sides by v and multiply both sides by du, but we also need to divide both sides by u as well. So what we get if we simplify this equation, this differential equation, we get dv over v, which is equal to a half of du over u, and we always put in our integral signs, and then we can integrate. So what we've got here is the log of the mod of v, which is equal to the half of logarithm. I don't like my logarithms like that, so if we write logarithm of u plus, well, we have to have a constant here, so I'll just put an a there, but it's not very helpful calling it an a. We could call it something more convenient, like, for example, we'll just choose a half log of C2 in this case. Have I already used C2? Let's have a look. No, we've used C1 up there, and we've got a C2 there. That's okay. So I've just manipulated this constant to read a half log C2 because we've got a half here in front of the logarithm of u term. So it helps to have a half of logarithm of whatever term this is here, because when we take anti-logarithms, we've got v equals, well, let's just not jump the gun too much. We'll just write down log of v equals the log of u to the half plus log of C2 to the half. Okay, right, that's what you can do with logarithms. And simplifying a bit further, we can have log of v equals the log. Now you can multiply the u and the C2 together to get u C2 to the half, and if we come down here, we've got log, I'll just rewrite it again, log of v equals log of C2, let me just get rid of that. Right, okay, just making mistakes as usual. So we've got u here to the power half, and what you do, you can take anti-logarithms to get v equals C2 u, and we want that to the power a half. Okay, now this can be expanded as C2 to the half times u to the half. U to the half, that's just square root of u, but anyway, we'll leave it as that for now. So v equals, well, we'll call this C2 to the half constant as C3. So we've got C3 times u to the half, and we know from above, because we've defined this to be the case, that but v equals du by dx. So this implies that du by dx equals C3u to the half. Okay. Therefore, separating the variables again, we've got du over u to the half integral of equals C3 times dx, right? If you've done elementary calculus, you will know how to solve this. It's u to the minus a half du equals C3 times the integral of dx, and that simply comes out to be u. What's minus a half plus 1? Well, it's a half. And that's equal to C3x plus another constant C4. Okie doke. Now, we know what u is because u is equal to 2y minus 3. So we have 2y minus 3 all to the power of half equals C3x plus C4. Now, we don't have any initial conditions or anything like that. So what I'll just do is to quickly simplify this equation and make y the subject of it. So we'll call this equation 3. I hope we haven't already got an equation 3. I'll just have a look up there. Right, so we've got a 2 there. So what we want to do is, so let's get that square. Squaring both sides of 3, we get 2y minus 3 equals c3x plus c4 all squared. Oops, excuse me. That's there we are. Right. Oop. Made a bit of a mistake there, didn't I? So squared. Okie doke. Right. So we'll just leave the part on the right hand side squared. It's actually a quadratic equation. So just simplifying a bit further, we have 2y equals 3 plus, in brackets, c3x plus c4 all squared. And then we want to divide both sides by 2. So we have y equals 3 over 2 plus a half of c3x plus c4 all squared. So we'll just conclude by saying that actually there are 2 solutions, but one of them is a special case of the general solution, where we have 2 solutions. So we have a special case which is y equals a half 3 plus c1. So this is, I'll just write it here, special case of the general solution. Right, okie doke. And general solution, what have I got here? Excuse me. So we got y, make that look a bit, y equals 3 over 2 plus, what do I have up here? I think it's c2 plus c3x plus c4, c3x plus c4 all squared, and this is the general solution. There we are. I can't spell, can I? Right. So, and those are the solutions to equation 1 right at the top that we had at the beginning of the presentation, which was that. So the solutions to that are that, and you could, if you want, graph them and see what they're doing. In the first case of y equals a half of 3 plus c1, then that's quite easy to graph, because what you've got is, well, we'll just write it here, y equals 3 over 2 plus a half of c1. Well, this is all just equal to some constant, we'll call it a. And I want to check that I've got the right thing there. A half, 3 over 2 plus a half of c1. So if this is y and this is x, then all you're going to have is a constant line going across the graph like that. With the general solution, that's just a little bit more complicated. What you're actually going to get is probably something of quadratic form, which we could plot. You've got y on the vertical and right, so we've got y on the vertical here. Let's just right, so y on the vertical there and x on the vertical there, and usually quadratic graphs do something like that, or that's if they've got complex roots, or it might do something like that, or it could be over here, depending what the constants are, you know, or it might even be over here. So basically, that is the way to solve that equation. But I hope that's been helpful, and do tune in again, and I hope to see you soon. But thank you very much. Bye for now.